August 1943, New Georgia. Solomon Islands. The jungle canopy is so thick that noon feels like twilight. Technical Sergeant James Callahan crouches behind a massive banyan tree, 38 pounds of SCR 300 radio strapped to his back, watching his company commander try to coordinate an artillery strike through hand signals, because the radio keeps cutting out at 400 yards. The mathematics are brutally simple. The official manual says 3 miles maximum range. In this terrain, with mountains and vegetation between the transmitter and receiver, Callahan gets maybe a quarter mile of reliable communication before the signal dissolves into static. The Motorola engineers back in Chicago designed this radio for European fields and North African deserts. Nobody told the jungle. His company is pinned down by a Japanese machine gun nest positioned on high ground. Battalion headquarters sits 2 miles back, well within the theoretical range of the SCR 300. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But theoretical and actual are different countries when you're trying to push radio waves through triple canopy rainforest, where every leaf is a tiny antenna absorbing your signal. Callahan knows what the problem is. Everyone who carries these radios knows. The AN 130 antenna, that 33-inch whip that telescopes out from the transceiver, is electrically short for the 40 to 48 MHz frequency range. It's a compromise between portability and performance, and right now, the compromise is getting Marines killed. The signal core has another antenna, the AN 131, a full half-wavelength monster that extends to 10 feet 8 inches when assembled from 9 separate sections held together by stainless steel cord. Callahan has one in his pack. He's not supposed to use it during movement because it's conspicuous, draws enemy fire, and makes him look like a mobile flagpole. But his current antenna isn't reaching battalion, and without artillery support, his company is going. To spend the night in this miserable position listening to Japanese patrols probe their perimeter, he makes a decision that technically violates field protocol. He assembles the long antenna. Within 90 seconds, he's talking to battalion. Within 5 minutes, artillery rounds are screaming overhead, walking up the hillside toward that machine gun nest. Within 10 minutes, his company is moving forward. Nobody writes him up for using unauthorized equipment. They should have, according to regulations, but everyone understands that survival trumps procedure every single time. This is the dirty secret of every radio war. The equipment works until it doesn't, and when it doesn't, somebody has to fix it with whatever materials are available and whatever knowledge they can improvise. The engineers can't anticipate every terrain, every weather condition, every tactical situation that will stress their designs past the breaking point. This isn't the story of one man's band modification. It's bigger than that. It's the story of how battlefield necessity drove hundreds of small innovations that collectively transformed military radio from a headquarters luxury into a squad-level necessity. And it starts 2 years earlier, in a cramped engineering lab in Chicago, where the fundamental problem wasn't range. It was whether portable battlefield radio was even possible. 1941. Daniel Noble sits in his office at Galvin Manufacturing Corporation, known to the public as Motorola, staring at a specification document that might as well be asking him to design a flying car. The U.S. Army Signal Corps wants a portable, battery-powered radio that infantry can carry into combat, not vehicle-mounted, not telephone wire. An actual wireless transceiver, small enough for one man to haul through mud and mountains, while also carrying rifle, ammunition, rations, and all the other equipment that turns modern soldiers into pack animals. The specifications are precise and demanding. Maximum weight 35 pounds including batteries. Operational range 3 miles minimum. 41 selectable channels in the 40 to 48 MHz band. Frequency modulation to reduce interference. Waterproof enough to survive tropical downpours. Rugged enough to survive being dropped, kicked, and generally abused by exhausted men under fire. Noble is an engineer who understands that specifications and reality often live in different zip codes. He joined Motorola 8 months earlier, right around the time the company received a contract to develop the SCR 536 handy-talkie, a 5-pound handheld AM radio that could fit in one hand. The 536 worked, technically. It transmitted and received voice communications, but its effective range was measured in hundreds of yards, maybe a mile over flat terrain, 3 miles over water if conditions were perfect and you sacrificed a chicken to the radio gods. The army wanted something with real reach, something that could link frontline troops to headquarters without requiring a communications sergeant to string telephone wire through hostile territory. Wire was reliable when it stayed intact, but wire got cut by artillery, severed by tank treads, and generally failed at the worst possible moments. Noble assembles his team, Henrik Magnuski, the RF radio frequency engineer who actually understands how to make radio waves do what you want instead of what physics prefers. Marion Bond, Lloyd Morris, and Bill Vogel round out the group. They're young, most of them, university-trained but not yet hardened by the kind of soul-crushing failures that teach you what's actually impossible versus what's just really difficult. The first question they tackle is frequency. The SCR 536 handy-talkie operates in the 3.5 to 6 MHz range, basically just above the AM broadcast band. Low frequency means long wavelengths, which means you need enormous antennas for efficient transmission. The 536 has a 40-inch telescoping whip, and even that is woefully inadequate for the frequency it's trying to radiate. It's like trying to throw a baseball with a straw for an arm. Noble decides to go VHF, very high frequency, 40 to 48 MHz. Higher frequency means shorter wavelengths, which means smaller antennas can actually work properly. More importantly, VHF at these frequencies doesn't bounce off the ionosphere like low-frequency HF signals. VHF is line of sight, which sounds like a limitation until you realize that in combat, line of sight usually means you can see the person you're trying to talk to, and that's exactly the tactical problem the army is trying to solve. The second major decision is frequency modulation instead of amplitude modulation. This is Noble's specialty, his obsession. FM is newer technology, less proven, but it has one massive advantage. It's inherently more resistant to electrical interference. Every vehicle, on a battlefield, generates ignition noise. Every time a tank starts its engine or a truck changes gears, it creates electrical hash that obliterates AM signals. FM doesn't care nearly as much. You can run an FM radio next to a convoy and still hold a clear conversation. The team builds their first prototype in early 1942. It's housed in a wooden box that looks like something you'd store tools in, which is appropriate because the circuit boards inside are basically hand-built, using whatever components they can source from suppliers, already stretched thin by wartime production demands. The transmitter section uses 18 vacuum tubes. That's a staggering number for a portable unit. Each tube is a potential failure point, a fragile glass envelope filled with heated filaments and delicate internal structures that hate vibration, temperature swings, and moisture. But in 1942, vacuum tubes are the only game in town. Transistors exist only in theoretical papers, and won't become practical for another decade. The power requirements are substantial. Those 18 tubes need both filament voltage and plate voltage, which means 2 separate battery systems. The Army supplies them with lead-acid batteries, borrowed from vehicle systems, and carbon-zinc dry cells, that together weigh more than the radio itself. With the large BA-70 battery, the complete system tips the scales at 38 pounds. With the smaller BA-80 battery, you can get down to 32 pounds, but battery life drops from 40 hours to maybe 20. Testing begins at Motorola's Chicago facility, then moves to an open field outside the city. The results are simultaneously encouraging and humbling. In flat, open terrain with both radios using the full 10-foot AN-131 antenna, they achieve reliable communication at 8 miles. That's more than double the Army's specification. Noble is jubilant. Then they test in wooded terrain. Range drops to 4 miles. They test with one, radio elevated, and one at ground level. Range drops to 3 miles. They test with both radios in low areas, simulating troops operating in valleys or ravines. Range collapses to under 2 miles, sometimes less. This is the nature of VHF propagation, and every radio engineer knows it, but knowing it and experiencing it are different things. VHF doesn't bend over hills like lower frequencies. It doesn't penetrate dense foliage particularly well. It travels in straight lines, and anything solid between transmitter and receiver blocks the signal. Put a mountain between two SCR 300 radios, and they might as well be on different planets. The Army understands this limitation. They're not expecting miracles. What they want is reliable short-range tactical communication, and the SCR 300 delivers that. The critical acceptance tests happen at Fort Knox, Kentucky, in the spring of 1942. Infantry board observers, Signal Corps officers, and tactical commanders put the prototype through scenarios designed to break it. They run the radios continuously for 12-hour shifts. They drop them. They drag them through mud. They operate them in rainstorms. They set up interference generators to simulate battlefield electrical noise. Through all of it, the SCR 300 maintains clear communication. The FM design proves its worth. While AM radios dissolve into hash and static, the FM signal locks on and holds steady. Colonel O'Connell, who's been shepherding this project through the Signal Corps bureaucracy, watches the demonstrations with the kind of grim satisfaction that comes from finally seeing a piece of equipment that doesn't immediately fail in field conditions. He's seen too many promising radios perform beautifully in labs and catastrophically in actual use. The SCR 300 works. Motorola receives production authorization. By July 1942, they're manufacturing units. By the end of 1943, they'll have produced nearly 50,000 SCR 300 radios, each one hand-assembled, each one individually tested, each one shipped to some corner of the world where American forces are fighting. The radio goes to war in August 1943, hitting the Pacific Theater first. New Georgia becomes the proving ground, and the reports that flow back to the Signal Corps are mixed. The radio works. That's the good news. It maintains communication through conditions that would destroy AM equipment. The bad news is that 3 miles might as well be 30 miles when you're trying to coordinate between units separated by jungle, mountains, and the general chaos of combat operations. Lieutenant Colonel Ankenbrandt sends a message to General Meade after the first month of combat use. They are exactly what is needed for frontline communications in this theatre. Then he adds the qualifier that every engineer dreads. The main difficulty is keeping them supplied with fresh batteries. Battery life becomes the operational bottleneck. 40 hours. Sounds generous until you realize that combat operations don't run on schedules. A radio operator can't just turn off his equipment because the battery is getting low. He needs to maintain communications during firefights, during artillery barrages, during those long dark hours when Japanese infiltrators are probing the perimeter, and every rustle in the jungle might be an enemy patrol. Fresh batteries become as critical as ammunition. Supply sergeants prioritize them accordingly. The Signal Corps establishes battery replacement as a high-priority supply item, right alongside rations and medical supplies. Dead radios are worse than no radios, because they create the illusion of capability while delivering nothing. The antenna problem reveals itself gradually. The standard AN 130, that 33-inch whip, works adequately in open terrain. In jungle, in mountains, in urban combat where buildings block line of sight, it's marginal. Radio operators learn to improvise. Some attach their antennas to tree branches, gaining height and therefore range. Some run wire from the antenna base to elevated positions, essentially creating makeshift long-wire antennas. Some discover that placing the radio on high ground or even on top of vehicles improves performance dramatically. These aren't band modifications. They're field expedients, the kind of practical adaptations that soldiers make when official doctrine meets real-world conditions. Signal Corps technical bulletins start accumulating reports from various theatres. Company commanders submit after-action reports noting that, reception improved when aerial placed out second-story window, or range extended by substituting German wire to helmet strap. The Signal Corps response is bureaucratically perfect. They note that the SCR-300 has a tuned antenna and that variations in length may reduce transmission range. Then they don't actually forbid the modifications because they understand that forbidding would be pointless. Soldiers in combat will do whatever works, and trying to enforce antenna regulations on troops under fire is a losing proposition. What emerges from 1943 and 44 is a pattern. The SCR-300 as designed performs exactly as specified in the scenarios that Motorola and the Signal Corps anticipated. But war is fought in scenarios nobody anticipated, and that's where the problems appear. The radio works brilliantly for coordinating platoon movements in French farmland. It struggles in the Ardennes forests. It performs well in Italian valleys and poorly in Italian mountains. It excels during amphibious operations, where line of sight extends for miles over water, and it falters in Pacific jungles, where visibility extends to arm's reach. This is the fundamental tension in every piece of military equipment. You design for specifications, but specifications can't capture the infinite variability of actual combat. The engineers did their job. They built a radio that met every requirement. But meeting requirements isn't the same as solving problems, and the problems that needed solving kept evolving with every new theatre, every new terrain, every new tactical situation. The European theatre of operations provides different challenges. When American forces hit Normandy beaches in June 1944, every rifle company has SCR-300 radios. The 29th Infantry Division lands at Omaha Beach with handfuls of SCR-536 handy-talkies and several SCR-300 backpack radios per company. The beach assault reveals range limitations immediately. Units spread across the beach can't maintain contact. The cliffs behind the beach block signals. Radio operators find themselves running, actually sprinting while carrying 38 pounds of radio equipment, trying to maintain physical proximity to their commanders because radio proximity isn't working. Once inland, the situation improves and then deteriorates in new ways. The hedgerow country of Normandy, those ancient field boundaries made of earth embankments topped with dense vegetation, creates a communications nightmare. Each hedgerow is a barrier. String a dozen hedgerows between two units and radio range collapses. An SCR-300 that should reach 3 miles barely manages 300 yards. Radio operators adapt. They learn to position themselves at the highest point available. They climb trees, despite that making them conspicuous targets. They run antennas up barn walls or church steeples. They discover that metal roofs and water towers, basically anything that provides height and reflective surfaces, extends range. Staff Sergeant George Bromwell of the 29th Infantry Division learns an expensive lesson about antenna visibility. He's carrying his SCR-300 during an attack, positioned behind a hedgerow. He switches from the short AN-130 antenna to the long AN-131 because he needs to reach battalion headquarters. Within 2 minutes, German mortars start dropping on his position. Somebody points out that his 10-foot antenna is sticking up above the hedgerow like a billboard, advertising, "Radio operator here, please shell this location." From that moment, Bromwell becomes paranoid about antenna concealment. Communication personnel throughout the theatre learn the same lesson. The radio's effectiveness and the operator's survival exist in direct tension. You need the long antenna for range, but the long antenna makes you a target. The problem intensifies in the Ardennes offensive, the Battle of the Bulge in December 1944. Winter weather degrades battery performance. Cold temperatures reduce chemical reaction rates in carbon-zinc cells, cutting usable capacity by 30 to 40%. Radio operators find their 40-hour batteries dying after 25 hours. Replacement supplies can't keep up with demand because nobody anticipated the intensity of operations or the battery degradation from cold weather. The Signal Corps scrambles. They establish priority supply channels specifically for radio batteries. They arrange air transport for critical deliveries. By late January 1945, battery availability improves, but the supply crisis exposes a fundamental weakness. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The SCR-300 is only as good as its power supply, and power supply logistics in combat conditions are brutally difficult. Range remains the persistent problem. 3 miles sounds adequate until you realize that tactical situations routinely separate units by 5, 6, 8 miles. Mountain warfare in Italy stretches the radios past their design limits. Urban fighting in German cities creates signal shadows, where buildings block transmission. Every theatre develops its own workarounds, its own field expedients, its own locally developed wisdom about how to make the equipment perform better than specifications promise. Some units start mounting SCR-300 radios on jeeps, using vehicle batteries for extended operation and vehicle height for improved antenna positioning. This isn't in the manual, but it works. Some artillery forward observers rig wire extensions from their radios to elevated antenna positions, effectively creating remote transmitter installations. This definitely isn't in the manual, but it saves lives by maintaining communication when direct antenna connection fails. The Pacific Theatre faces different challenges but reaches similar solutions. Island warfare means units can use water propagation to their advantage. VHF travels extremely well over water because there's no terrain to block line of sight. SCR-300 radios operating during amphibious assaults routinely achieve 10 to 15-mile ranges, double or triple the normal specification, because transmitter and receiver are elevated on ships and landing craft with nothing but flat ocean between them. Technical Sergeant Callahan, who started this story crouched in New Guinea jungle, survives the war. He carries his SCR-300 through New Georgia, Bougainville, and finally Luzon in the Philippines. He becomes expert at reading terrain, at understanding exactly where to position himself for maximum radio effectiveness. He learns that valleys are death to communications and hilltops are survival. He learns that morning humidity degrades performance and afternoon heat sometimes improves it through atmospheric effects nobody fully understands. He submits exactly 0 reports about his techniques because most of what he does contradicts official procedure. He uses antennas that aren't authorized for specific situations. He positions himself in locations that are tactically questionable but radio optimal. He runs his radio at power settings that drain batteries faster than recommended because dead batteries tomorrow don't help when you need communications today. This is the real story of battlefield radio in World War II. Not one band modification that changed everything, but thousands of small adaptations that collectively transformed equipment performing at specifications into equipment performing at necessity. The engineers gave them radios that worked. The soldiers made them work better, or at least work differently, in ways that met actual combat requirements rather than theoretical specifications. By May 1945, the war in Europe ends. By August, the Pacific War concludes. Motorola has produced nearly 50,000 SCR-300 radios. Those radios coordinated artillery strikes, called in air support, maintained tactical communications, and generally kept American forces connected in ways that previous wars couldn't imagine. They weren't perfect, they had limitations. But they were there, they worked, and when they didn't work quite well enough, somebody figured out how to make them work better. March 1944. Somewhere in the Italian Apennines. The 10th Mountain Division is preparing for operations at elevations where breathing is hard and radio communication is supposedly impossible. Captain Robert Morrison, the division signals officer, has a problem that looks unsolvable on paper. His infantry companies will be operating on mountaintops separated by valleys 2, 3, sometimes 4 miles wide and 2,000 feet deep. The SCR-300's 3-mile range assumes relatively flat terrain. Put mountains between the radios and the effective range collapses to nothing because radio waves don't bend around granite. Morrison spends a week analyzing the terrain, studying topographical maps, and doing calculations that probably would have gotten him laughed out of engineering school. He realizes something that seems obvious in retrospect, but wasn't obvious until somebody thought about it. The problem isn't the radio's power or the antenna's efficiency. The problem is trying to push signals through valleys when valleys are natural signal sinks. Solution: don't transmit through valleys, transmit over them. He establishes relay stations, takes spare SCR-300 units, positions them on the highest points available, and sets them up in pairs. One radio receives on channel 15, the other transmits on channel 30. Incoming signal from a forward unit gets picked up by the receiving radio, then immediately retransmitted by the paired radio on a different frequency to headquarters. It's not elegant. It requires dedicated radio operators sitting on cold mountaintops doing nothing but relay work. It eats through batteries like a starving man at a buffet. But it works. Forward observers can call in artillery from positions that should be completely cut off. Companies can coordinate movements across terrain that should make coordination impossible. The Signal Corps eventually catches wind of this and publishes it as an official technique in technical bulletins. But Morrison figured it out months before the official guidance reached Italy, because waiting for official guidance means people die while you're waiting. This is the pattern that repeats across every theatre. Individual signal officers, radio operators, even infantry commanders who barely understand how radio works, they all start experimenting. They try things that aren't in manuals. Most attempts fail. Some work. The ones that work get shared, person to person, unit to unit, faster than official communications could ever distribute them. In the Pacific, marine radio operators discover that coconut trees make excellent improvised antenna masts. The trunks are tall, straight, and relatively easy to climb. Run a wire from your radio to the top of a coconut palm, and your 3-mile range suddenly becomes 6 or 7 miles because you've elevated your antenna 60 feet above ground level. Nobody tells them to do this. They just figure it out through trial and error, the same way humans have solved problems since before we invented radio. In France, Signal Corps technicians learn that German telephone wire, the stuff they scavenge from captured positions, has better electrical properties than some American wire they've been issued. The German wire is heavier gauge, better insulated, more flexible in cold weather. They start using it for antenna extensions, for ground planes, for basically any application where wire quality matters. Technical Sergeant William Hendricks, stationed with the Third Army during the advance through France, keeps a notebook where he records every modification, every field expedient, every trick that works. His notebook becomes legendary in his battalion. Other radio operators copy his notes by hand. Some of his techniques directly contradict official guidance, which states that antenna modifications will reduce performance. Hendricks's position is simple. Official guidance is written by engineers in comfortable offices who've never tried to coordinate tank movements through a thunderstorm with enemy artillery bracketing your position. He'll take performance that works over performance that's theoretically correct any day. One of his innovations becomes widely adopted, though never officially recognized. He discovers that connecting the radio's ground terminal to any large metal object, a vehicle chassis, a steel fence post, even a pile of barbed wire, improves both transmission and reception. The metal provides what radio engineers call a counterpoise, an artificial ground plane that helps the antenna radiate more efficiently. This isn't secret knowledge. Any electrical engineer could explain why it works, but it's not in the SCR-300 technical manual, so thousands of radio operators never think to try it until somebody like Hendricks experiments and shares the results. The ammunition shortage during the Battle of the Bulge creates an unexpected radio crisis. Supply priorities shift heavily toward ammunition and fuel. Everything else, including radio batteries, drops down the list. Radio operators face impossible choices. Run the radio to maintain communications and risk having a dead battery when you desperately need it, or conserve battery power and accept degraded communications now. Some operators start carrying multiple battery sets, even though each BA-70 battery weighs 6 pounds, and carrying extras means less ammunition or rations. Some units establish battery charging stations using captured German equipment or improvised systems built from vehicle alternators. None of this is official. All of it is necessary. By early 1945, the aggregate knowledge of how to actually use SCR-300 radios in combat has diverged significantly from the official technical manual. The manual still describes a radio with 3-mile range, 18-tube FM transceiver, 41 channels, operates on battery power. That's all true. What the manual doesn't describe is the accumulated field wisdom about antenna positioning, terrain analysis, relay techniques, battery management, and the hundreds of small tricks that separate radios that barely work from radios that keep units alive. The Signal Corps begins collecting after-action reports more systematically in mid-1944. They're trying to understand why some units report excellent SCR-300 performance while others report chronic problems. The answer, they discover, isn't in the equipment. It's in the operators and their commanders. Units with experienced signal officers who encourage improvisation, who allow radio operators to experiment, who don't rigidly enforce technical manual procedures. These units report good communications. Units with rigid command structures that demand everything be done by the book, these units struggle. This creates a quiet revolution in Signal Corps doctrine. The realization that equipment performance depends less on design specifications and more on user adaptation fundamentally changes how they approach training. Post-war technical schools will emphasize field expedience and creative problem-solving over rote memorization of specifications. The legacy of the SCR-300 extends far beyond World War II. The radio itself continues in service through the Korean War, finally being replaced by the AN, PRC, 8, 9, and 10 series in the early 1950s. But the real legacy isn't the hardware, it's the operational philosophy. Before the SCR-300, radio communication was a headquarters function. Battalions had radios, maybe companies had radios if they were lucky. Individual squads communicated by runner, by hand signal, by shouting. The SCR-300 pushed radio down to company level as standard equipment. More importantly, it demonstrated that portable tactical radio was actually possible. The post-war development of handheld radios, the eventual AN, PRC-6 and its successors, all trace their lineage to lessons learned from the SCR-300. Weight needed to come down, battery life needed to improve, range needed to extend. But the fundamental concept that individual soldiers could carry their own communications equipment and coordinate in real time without wire, that concept came from those 50,000 SCR-300 radios carried through jungles, mountains, deserts, and cities from 1943 to 45. Daniel Noble receives the Army's Certificate of Merit for his role in developing the SCR-300. He accepts it with characteristic modesty, immediately crediting Magnuski, Vogel, Morris, and Bond. He adds something that gets quoted in Motorola's internal histories. The development of the walkie-talkie was an academic exercise compared to the contribution of the men on the battlefields, the men fighting the war. He's right, of course. The engineers designed a radio that worked. The soldiers made it work everywhere, under conditions the engineers never imagined. That's not a failure of engineering. That's the nature of war. You can't test for every scenario in a laboratory. You can only design equipment robust enough that when soldiers inevitably push it past specifications, it doesn't catastrophically fail. The SCR-300 had that robustness. Drop it in mud, it still worked. Get it soaking wet, it still worked. Run it continuously for 30 hours straight, it still worked. The vacuum tubes were fragile in theory, but survived shocking abuse in practice. The waterproofing held up through monsoons and winter storms. The construction was solid enough that radios recovered from destroyed vehicles could often be cannibalized for parts to repair other units. Technical Sergeant Callahan, who we met at the beginning in that New Georgia jungle, returns home in December 1945. He'll carry a piece of that SCR-300 experience for the rest of his life. The weight on his back, the constant awareness of terrain and how it affects signals, the muscle memory of extending that antenna while simultaneously hitting the ground when incoming fire starts. He never writes a book about his experiences. He never publishes technical papers about field-expedient antenna modifications. He goes back to civilian life, works an electrical contractor in Ohio, occasionally tells stories about the war when someone asks. The radio equipment he carried becomes obsolete, replaced by newer designs with better specifications. But the principle he lived by, that specifications are starting points rather than limits, that necessity drives innovation faster than engineering committees ever could, that principle becomes embedded in military communications doctrine. Modern tactical radios are designed with the explicit understanding that soldiers will use them in ways designers never anticipated, and the equipment needs to be flexible enough to accommodate that creativity. The story of the SCR-300 isn't really about one band modification that changed everything. It's about 1,000 permitted adaptations that collectively transformed battlefield communications. Nobody forbade the modifications because the modifications were necessary. The Signal Corps understood what Callahan and Morrison and Hendricks and thousands of other radio operators figured out through experience. Official doctrine is useful right up until the moment it contacts reality, and at that moment, reality wins every time. The engineers gave soldiers a radio with 3-mile range. The soldiers figured out how to push it to 5 miles, 8 miles, sometimes 15 miles over water, by understanding terrain, by experimenting with antennas, by positioning themselves intelligently, by using relay techniques, by doing everything except accepting that 3 miles was some kind of hard limit. That's the lesson. Not that one person's clever hack changed the war, though individual innovations certainly mattered. The real lesson is that equipment capabilities are negotiable when the people using the equipment refuse to accept limitations. The SCR-300 had a specified range. It also had an actual range that depended entirely on who was operating it and how creative they were willing to be. 50,000 radios, thousands of operators, hundreds of innovations, most never documented, many contradicting official guidance, all of them necessary. That's how you transform a 38-pound backpack radio with theoretical 3-mile range into a communication system that actually kept American forces coordinated across the most challenging terrain on Earth. The wooden box prototypes that Noble's team tested outside Chicago in 1942 barely resembled the combat-worn, improvised, jury-rigged radios that came home from Europe and the Pacific in 1945. Same model number, same basic electronics, completely different equipment because the soldiers had modified, adapted, and improved everything they could reach. Nobody banned these modifications because banning them would have been pointless. You can't enforce regulations on troops in combat who are trying not to die. You can only build equipment strong enough to survive their creativity and hope they use that creativity to win. The SCR-300 was strong enough. The soldiers were creative enough. And together, they proved that the distance between official specifications and actual necessity is exactly as far as human ingenuity can bridge when survival depends on it. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.